Our next topic is finding the position of maximum shear stress and finding the maximum shear stress in magnitude. So our topic is maximum shear stress. Position means angle at which it acts. The maximum shear stress acts that position, the angle. So we are taking the generalized case in which the normal stresses are on the mutually perpendicular planes and shear stresses are also acting like this. This is our most general case. Shear stresses are acting on this plane. This is tau, this is tau. These are the shear stress acting on this plane. And we want to find out that position where maximum position shear stress is acting, right? So suppose this is that angle where maximum shear stress is acting, right? So whatever shear stress is there, this is the maximum shear stress, tau max or sigma t max. And there will be some normal force also, normal stresses also. It doesn't mean that there will be no normal stress. There will be some normal stress on this plane. So our aim is to find out the plane on which the maximum shear stress is acting, sigma t max is acting, right? And we can also find out the normal stress on this plane. So when there is principal stress, there is no shear stress. Principal stress means maximum or minimum shear stresses, normal stresses. So when there is maximum normal stress, there is no shear stress. But the reverse is not true. When there is maximum shear stress, there are some normal stresses also, right? Let us find out the plane. We know that for maxima, the slope of something should be equal to 0. So as we have obtained the maximum normal stress or principal stress by differentiating the shear stress with respect to theta, so that was equal to 0. So in the same case, we are differentiating the shear stress, the value of shear stress with respect to theta, right? And that should be equal to 0. So differentiate the sigma t, this is sigma t. We have used a term sigma t, right? That's why I am using sigma t here. So differentiate sigma t with respect to theta and equate to 0, and we will get the plane of maximum shear stress. The whatever value of theta we get, that will be the value where the shear stress is maximum. So d sigma t by d theta will be equal to 0. Now what is the value of sigma t? Sigma t value. So sigma t, our sigma t was minus sigma x minus sigma y minus sigma x minus sigma y by 2 sine 2 theta plus tau cos 2 theta. This was the formula for our tangential stress sigma t at a certain plane. And now we want to find out the maximum value. What is the maximum value? What is the maximum value of this sigma t max? This we want to find out. So for maxima, we can differentiate it with respect to theta and find out the and equate to 0. So differentiate it. So d sigma t by d theta will be equal to minus sigma x minus sigma y by 2 sine 2 theta is 2 cos 2 theta plus tau minus 2 sine 2 theta, because the differentiation of cos theta 2 theta is minus 2 sine 2 theta, isn't it? And this value should be equal to 0. This value should be equal to 0 for maximum for the plane of maximum shear stress. So from here we can find out what we can get is 2 to 2 cancel, and you will get, take sine theta on one side and cos 2 theta on another side. So we will get minus 2 tau sine 2 theta will be equal to minus, and this, when this will come to this side, it will become positive. So this will be plus sigma x minus sigma y, and 2 is already vanished. So sigma x minus sigma y cos 2 theta. So divide cos 2 theta by sin 2 theta, it will become tan 2 theta. So you will get tan 2 theta. Now this is theta s, because now it is the plane of maximum shear stress, and that will be equal to sigma x minus sigma y by, and that minus, because there is minus sign, sigma x minus sigma y upon 2 tau. So this is the value of tan 2 theta s, the plane where maximum shear stress is acting. So you have to remember this. This is very important result. You have to remember this. Or theta s can be find out from here. You will get the theta s will be equal to half of tan inverse of minus sigma x minus sigma y by 2 tau. This is the plane of maximum shear stress. So better to remember this. Better to remember this equation. It is easy to remember. You can see here, this is just reverse of tan 2 theta p. This is just reverse of tan 2 theta p with negative sign. Here there is negative sign, and in that case it was 2 tau by sigma x minus sigma y with no negative sign, that was positive. So these are the equations. Sigma t was the tangential stress at this angle, at any angle. This was the equation, and we have found out that tan 2 theta s, the plane of maximum shear stress, right? So if we put this value 2 theta s value in this, we can find out the maximum shear stress sigma t max at this plane, theta s plane. So what we can do is, it is easy to have a triangle in which we can find out sin 2 theta and cos 2 theta. So let us have a triangle. This triangle has no connection with this triangle. We are making another triangle, arbitrary triangle, and the value of this angle is supposed 2 theta s, and this is 2 theta s, and our tan theta is perpendicular upon base. Our perpendicular is minus sigma x minus sigma y, sigma x minus sigma y. Base is 2 tau. So our base is 2 tau. So this is perpendicular, this is base, and hypotenuse will be square of this plus square of this under the root. So sigma x minus sigma y whole square plus 4 tau square. Now what is the value of sin 2 theta? Sin 2 theta. So what is the sin 2 theta and what is cos 2 theta? Sin 2 theta will be perpendicular upon hypotenuse minus sigma x minus sigma y by this, and cos 2 theta will be 2 tau upon hypotenuse, base upon hypotenuse. So we will put here these equations in one. So sigma t will be equal to minus sigma x minus sigma y by 2 sin 2 theta. Sin 2 theta is perpendicular minus sigma x minus sigma y upon base, hypotenuse, that is under the root sigma x minus sigma y whole square plus 4 tau square. This is our sin 2 theta. And what will be the cos 2 theta? That will be equal to tau times cos 2 theta base upon hypotenuse, that is under the root sigma x minus sigma y whole square plus 4 tau square. So this is our equation after substituting the value of sin 2 theta and cos 2 theta. Now what is sigma t again? Now it will become sigma t max, maximum shear stress, right? So sigma t max, this is basically sigma t max. In the last we can write this. So what is maximum shear stress? That is will be equal to, here sigma x minus sigma y by 2, here sigma x minus sigma y plus 2 tau. So we can take half outside this bracket even minus half, minus and minus will become plus. So half can be taken outside, 1 by 2 can be taken outside, this will become left and this will become the same unit, right? So what will happen like this minus and minus will become plus, this will be half, 1 by 2 can be taken out. In the bracket you will get sigma x minus sigma y whole square, sigma x minus sigma y whole square. As we have taken half outside, so it will become 4. So and tau will be tau square. So this will be 4 tau square upon under the root sigma x minus sigma y whole square plus 4 tau square. You can see here in numerator we have the some value and the same value we have in denominator with under root. So finally we will get sigma t will be equal to half of under the root sigma x minus sigma y whole square plus 4 tau square. This is basically sigma t max. So sigma t max we can write, further we can solve for simplicity. We can further solve that sigma t max, maximum shear stress at a plane at theta s, will be equal to, as you know, there are two types of shear stresses acting on this. One is the applied stress and one is the complementary shear stress, right? So here if we take one of the shear stress, and they are making two couples, here they are making two couples like this tau and this tau, these are making couple in anti-clockwise direction, and this tau is making couple in clockwise direction, right? So you can see here this is one couple tau and which is making anti-clockwise couple tau multiplied by area, that will make an anti-clockwise couple, and this is making another couple which is clockwise, right? So one of the couple we can take negative and one of the couple we can take positive. So let us take this anti-clockwise couple to be positive and clockwise couple to be negative, right? So anti-clockwise shear stress, basically shear stress is positive and clockwise as negative, right? So in this here we are putting the sign convention that this type of shear stress which is making anti-clockwise couple is positive, and here I am writing tau. Basically this is shear stress in anti-clockwise direction. Two couples are there, tau and tau, two are there, and the couple which is making clockwise rotation, basically it is shear stress, this is negative. This is our sign convention. You can choose your own convention. So here as we have used principal stresses plus and minus, here also we can use plus and minus. One is for positive couple and one is for negative couple. So similarly here also sigma t maximum, there will be shear stresses and complementary shear stresses. One of the shear stresses will be the positive, which according to sign convention, and one will be the negative depending on the couple it is making, right? If here it is anti-clockwise couple, that will be positive. If it is a clockwise couple at this point, it will be negative, right? So here if you want to see here, this is the stress element here, and there is some sigma t max here, you can see here sigma t max, and there will also be normal stresses also. It is not so that there are no normal stresses, there are normal stresses. Sigma n are also there, right? Sigma n are also there. So this type of stress is there, that one is positive and one is negative. That's why we are writing plus and minus, and we can write here under the root sigma x minus sigma y by 2 whole square plus tau square. So this is the equation which you have to remember. Maximum shear stress at a plane of theta s. This you have to remember, and this is very important. Maximum shear stress. So I want to separate these things actually. I want to separate so that it can be easily visible to you. Uh, here I want to make it a separation so that you may not confuse between the, right? So this part is separate, this is the derivation, and this part is a basic concept which we have used to derive this equation. So this equation you have to remember. As we have discussed earlier that on the plane of maximum shear stress there are some normal stresses. It is not the case like principal stresses that in case of principal stresses these are maximum shear stress, maximum normal stress, and on the plane of maximum normal stress there is no shear stress. Shear stress at that plane is 0. But it is not the case with tangential stresses like this, that sigma t is maximum but there is some normal stresses sigma n, and our aim is to find out that normal stresses on the plane of maximum shear stresses, right? So we have obtained this result for the plane of maximum shear stress, that tan 2 theta will be given by this equation. Now if I put the value of 2 theta here in cos 2 theta and sin 2 theta, I will get the normal stresses on the plane of this theta s. Now because it is difficult to put 2 theta directly, what we can do is we have made this triangle and we have put the perpendicular, this tan 2 theta is perpendicular upon base, perpendicular is this, base is this, and hypotenuse we have obtained. Now sin 2 theta is perpendicular upon hypotenuse, cos 2 theta is base upon hypotenuse, right? So put the value of sin 2 theta from this triangle, cos 2 theta using this triangle, and put these values and get the value of normal stress. So let us see what we are getting. So sigma n will be equal to sigma x plus sigma y by 2 minus sigma x minus sigma y by 2 cos 2 theta. What is cos 2 theta? Base upon hypotenuse 2 tau upon sigma x minus sigma y whole square plus 4 tau square minus tau sin 2 theta. What is sin 2 theta? Sin is this upon this minus sigma x minus sigma y by under the root sigma x minus sigma y whole square plus 4 tau square. So this is our normal stress after putting the value of cos 2 theta and sin 2 theta. Let us further solve it to get more concise result. So what will be sigma n again? That will be equal to sigma x plus sigma y by 2 minus you will see an interesting fact here that 2 to 2 cancel, you will get here, what you are getting here is minus tau sigma x minus sigma y divided by under the root sigma x minus sigma y whole square plus 4 tau square, right? Minus and minus plus, so here plus, again tau, again sigma x minus sigma y, and again under the root in denominator sigma x minus sigma y whole square plus 4 tau square. You can see here this term and this term is exactly same, with this sum as negative sign and here it is positive sign. So this will cancel out, and what you will get in as a normal stress, that is sigma x plus sigma y by 2. So this is the normal stress on the plane of maximum shear stress, and let us give this normal stress the name as, so that it can be easily understood. This is sigma ns, the normal stress at the plane of maximum shear stress. Sigma ns I am writing here. So here also I am writing sigma ns. sigma ns belongs to the normal stress at the plane of maximum shear stress. So this is the sigma normal stress at the plane of maximum shear stress, and this is also very important and you have to remember it. This is very easy to remember. Just add up the applied forces sigma x plus sigma y and then take the average of this and you will get the normal stress on the plane of maximum shear stress. Now in this topic we want to find out the angle between these two planes. There is a plane of maximum shear stress and there is plane of principal stress. So what is the angle between these two? There is definite angle between the plane of maximum shear stress and plane of maximum principal stress or normal stresses, right? So what is a relation between these two angles? So here we want to find out this relation. So from this equation, these two equations we have already derived. This is the angle, theta p is the angle of principal plane and theta s is the angle of plane of maximum shear stress. So there is some relation between the two. What is that relation? You can see here tan 2 theta p, from this equation, tan 2 theta p is 2 tau by sigma x minus sigma y, and it is just reverse with negative sign, will be equal to minus 1 by tan 2 theta s. This is the relation between the two. It can be seen easily, right? Further we can write tan 2 theta p will be equal to, this will be cot minus cot 2 theta s. So further we can write 2 theta p will be equal to, tan 2 theta p will be equal to tan of, this is minus cot 2 theta s and this will be pi by 2 plus 2 theta s, right? So this will come into second quadrant. In second quadrant tan is negative and pi by 2 it will become cot. So tan 90 plus theta is equal to minus cot theta, right? You should remember that tan 90 plus theta will be equal to minus cot theta. This identity we have used here and we have converted minus cot theta into tan 90 plus theta. So here we have used pi by 2 plus 2 theta s. Now tan to tan cancel and we will get 2 theta p will be equal to pi by 2 plus 2 theta s, and theta p will be equal to the plane of maximum normal stress, principal plane. 2 divided, you can divide here, pi by 4 plus theta s. So there will be a 45 degree angle between these. So this will be 45 plus theta s, right? So principal plane will be 45 degree plus theta s. This is very important result. You can remember this.